Hi, I'm Michael Gilroy, and for my final project, I designed a mechanical steering system which could be implemented in any sort of small vehicle that wouldn't use regular power steering, like a go-kart, dune buggy, etc. I then built a model of my steering system, which I mounted on a full car frame, as you can see here, to show how it would actually work in terms of steering a car. And this was completely my design. Didn't come from any kind of set kit instructions of any kind. So anyway, let's take a closer look at my model. So here's a top view of my model, and as you can see, if I turn the steering wheel, the front wheels turn left and right as is expected, and so it does work pretty well for steering the car. As you can see, I turn the steering wheel and it controls the motion of the car. So as I said, I built a model of an entire car here to show how the steering system would work in terms of controlling a car, as I showed. But everything in black is just part of the car frame there to hold the steering system in place. What we're going to be focusing on are the colored parts, which is the actual steering system. I made each rigid body in my steering system a single color. So this whole red part right here is one rigid body, this whole yellow part is a rigid body, etc. So that will help show the parts that are connected together and move as one piece. So let's start by taking a look at the steering shaft, which is right here in red. As you can see, it consists of a steering wheel connected by a rod to a small gear, and they all move as a single part. So I turn the steering wheel, and this gear right here moves with the same angular velocity. So next we have this yellow gear, which is obviously larger than the red gear, 5 centimeters in diameter compared to 2 for the red gear. And the point at which they contact each other, obviously, as we learned in dynamics, those points have the same linear tangential velocity. But since the yellow gear has a larger radius, it ends up having a smaller angular velocity. The large yellow gear is then rigidly connected to this vertical bar that is mounted on, as well as these other parts. And so as you can see, when the yellow gear rotates, these parts rotate with it with the same angular velocity. So then we have this orange bar at the front of the vehicle, and as you can see, it's connected by a pin joint to the yellow gear. In my report I call this point A. And when the yellow gear is rotated, the orange bar moves in curvilinear translation, and the tangential velocity of point A is equal to the angular velocity of the large yellow gear times this radius, the length of this bar. So finally, we have the two wheel mounts here in red, and as you can see, the wheels are free to spin on the wheel mounts. The wheel mounts are connected to the car frame at these two pin joints, so they rotate about those joints. And then they're pinned to the front orange bar at the ends here. So I mounted the wheel mounts at the pin joints in line with the center of the yellow gear where it is mounted, and that makes these radii of rotation right here equal to the one right here of this yellow bar. And by doing that, by making the radii of rotation equal, that allows the orange bar to move in curvilinear translation, since all points on the bar are moving in curved path of the same radius. So once again, you can see the system as a whole works pretty well. Turns the front wheels left and right, and that allows the car to be steered pretty effectively. And so if this system were used in a real motorized vehicle, ideally the motor would be powering the back wheels, and then the steering would control the direction in the front. So now I'm going to perform a couple tests on my model. In my report, I calculated that if I turn the steering wheel 90 degrees, the front wheels should rotate to an angle of 36 degrees from their straightforward position. So we're going to test out that prediction. So here I have basically an expanded protractor that will help me measure wheel rotation. So let me set the car down here, and then I'm also going to put this little white piece on the top of the steering wheel so you can see its original position and then how far it's been turned. So that would be 90 degrees back to 0. So if we line the car up with the center right on the 0-degree line, right about there, and then I turn the steering wheel to 90 degrees, we can try to align the wheel with the degree marks. And as you can see, the angle of the wheel is somewhere right between 30 and 40 degrees, so 36 degrees looks just about accurate. And I can do the same in the other direction. That's about 90 degrees, and again, we see it's less than 40, more than 30, so 36 degrees looks like a good prediction. The other test I want to do on my model is how far the wheels themselves move during rotation. So for this, I'm going to use another blank sheet of paper. And in my calculations, I calculated how far the outside edge of each wheel at the center should move during a 90-degree rotation. So I'm going to start by making marks at the outer edge of each wheel. So right there, and right there, and then try to turn this 90 degrees without moving the paper too much. This isn't going to be a super accurate way of measuring, but it should give us some idea of how close I was with my calculations. So I'll make new marks at the outer edges at this point, so there, and right about there. So if I lift up my model, you can see, make the marks a little clearer. So if I measure those distances kind of along the same arc that the wheels were rotating, so it's just going to be an estimate, but I get about 2.3, 2.4 centimeters there, and about 2.2, 2.3 centimeters there. So both are pretty close to my calculated value of 2.2, within the range of error for the method I was using, but again, this was just to kind of show if my calculations were close, which they were. So I'll explain in my report the importance of both these measurements I just made and the corresponding calculations, but that's about it for testing the model. It looks like it works pretty well. The results are as expected. So, thanks for watching.